Hi, in this lecture, we are going to introduce the concept of voltage dividers and current dividers. And so this is going to be the part 3 of the fundamentals of voltage and currents, that lecture. So both the voltage dividers and current dividers are super important concepts. You need to know how that works, and in real applications, you are supposed to be able to use it really easily, not thinking about the equations and how to derive it, but just directly use it. That's a very basic um, requirements to be an electrical engineer. Okay. So let's look at voltage dividers first. So it looks like this. You have a power supply, which is the voltage source, and one resistor here to form a circuit. That's V, that's R1. Doesn't matter what's the value here. And this is, we call this is a V out. So that's the output voltage. So this is a input voltage, and there's a resistor network, and that's the output voltage. So the concept of the voltage dividers tell us V out compared to the ground. So whenever we just point to a voltage node in the circuit, okay, so this is a voltage node, right? That's a node. That's another node. You totally have 3 nodes here in this circuit. Node 1, node 2, node 3, because they have different voltages. So this is one voltage node. If I just point to this voltage node, I say the voltage here is called VL. I'm comparing this node to the ground. So that's how that works. So in the concept of voltage dividers, we V out here equals to V times R2 over R1 plus R2. Okay, so that's a concept for voltage dividers. And now let's derive it. Why this works in this way? Okay, so because you have 2 resistors and there's a battery in the circuit, so it's going to pump current flow in this direction in the circuit, and it's going to form 2 voltage drops. Okay, and in R2, right, specifically, because the current flows through R2 is also I, so the voltage across R2, which is exactly VL. Why is that? Because the anode terminal of the R2 is being shorted to VL. So if you compare this terminal to this terminal, it's exactly comparing V out to 0 volts. Okay, so the potential drop across R2 is exactly V out. So you are going to use, so VL is actually equals to I times R2, right? And if you look at the overall voltage, which is V, because that's a power supply, this is the highest potential in the circuit. And if you look at this resistor network has 2 terminals, and it has 2 resistors in series, and has the same current, which is also I. So V equals to I times R1 plus R2. So if you use left divided by the left and right divided by the right on the 2 sides of the equation, you are getting this. And I can be cancelled, right? And you move V to the other side of the equation, and you are eventually getting V times R2 over R1 plus R2. So that's the concept of voltage dividers. Compare here to here, they're the same equation. Okay, so this is a really important equation you want to use in the future. And after that, let's take a look at current dividers and how that works. So there is a current source. If I draw a circle and draw an arrow in the middle, so that means it's injecting a specific current into the circuit. Okay, I have two resistors in parallel. So R1, R2, and the current flows through R1 is going to be I1, and the current flows through I2 will be I2 because they are in different branches, so they have different current. Only when the two resistors are equal, they are getting the same share of the overall current flow in to this node, right? Being split into two branches. Only when you have two equal resistors, I1 equals to I2. However, it's not always happen, right? So now let's take a look at this. How do you derive the equation for the current divider? Because this is one voltage node, right? Make sure you understand this concept. They are one piece of metal until the resistor, because every time when it just goes across the resistor, there will be a voltage drop. However, before that, it's fine. They're all metal pieces, so they are sharing the same voltage potential, which is V, and this is ground. So for this entire circuit, only has two voltage nodes. One is V, one is 0 volts. Okay, so the V is created by the voltage drop of these two resistors, but they have the same V on the top. Okay, make sure you understand this concept first. And now we have, because we have derived the equivalent resistance for this resistor network when they're in parallel. So our equivalent of this resistor network is actually R1 plus R1 times R2 over R1 plus R2, because that's the equivalent resistance. If you treat the entire thing here as a black box, for example, if you treat here as a black box, then the two terminals, if you marry it, the resistance will be R equivalent, right? And the overall I is I, the current here. So you can say V is actually, so the V here, as this node, they're all the same voltage node. So V equals to I times R equivalent, which is I times R1 times R2 over R1 plus R2. So that's a V being calculated using I and R equivalent. And also they have the same V. For example, we just look at the first branch and has the same V, but however the current is just I1 and I1 R1, which is the resistance. So V also equals to I1 times R1. So no problem here, right? Look at these two are actually equal to each other. So if you write I times R1 times R2, R1 plus R2 equals to I1 times R1. And you can see that I1 can be cancelled on the two sides of the equation. So you have I1 left on the right side. So let's move it to the left side. So I1 equals to I times R2, R1 plus R2. So this looks like a similar structure compared to the voltage divider's equation. So you can see you have an output voltage equals to the overall voltage times R2 over R1 plus R2. But however, in the current divider's equation, you have the same R2 over R1 plus R2, but it's not I2, it's I1 here. Keep in mind. So the current flow in the current divider, because it's it's getting two branches of current flow through these two resistors respectively. So the current flows through I1 actually equals to the overall I times R2 on the top, but not R1. Keep in mind. So if we do the same way for the other side, so we are getting I times R1 times R2 over R1 plus R2 equals to I2 times R2, right? And R2 can be cancelled, so I2 equals to I you can expect R1 on the top. Keep in mind. So that's a current divider. All right. Let's look at some examples. So you can calculate the voltage at the output voltage node really quickly by using a voltage divider. Ten volts, and that's 5K ohms, another 5K ohms, and this is V out. So just let me know what is V out. Of course, just use a voltage divider equation. I'm having 10 volts times 5K here over 5K plus 5K. All right, so it is actually 5 volts. And another example. So V out equals to what? So definitely 3K on the top, which is 10 volts times 3K over 5K. And this is actually 6 volts. Right, so V out is 6 volts. And one more example for voltage dividers. Ground it. 5 volts. It's 2K. And 3K. So I'm going to introduce a different way. So when this will be super useful when you are working with the homework assignments. So if you have a circuit like this, the first step, keep in mind, step one. If you don't want to use voltage dividers, because sometimes the circuit can be complicated than this, so it's not real easy to use voltage dividers all the time. If you have something deep complicated, which is not this case, but just let you know, step one, calculate the current. Keep in mind, very, very important. Calculate the current. Step two, calculate the voltage drops. And if you get voltage drops for every single component, you can calculate everything in this linear circuit, right? So if you look at this circuit, the first step, let's get the I first. So I equals to 5 volts over 2K plus 3K, which is 1 milliamp, right? So you know there's a 1 milliamp current flows through this 2K resistor, which is going to create a voltage drop from here to here, and we call it V1. So V1 equals to 2K times 1 milliamp, which is 2 volts. So you got 2 volts here, and the same current flows through the 3K resistor, and you know the current is 1 milliamp, and so V2 equals to 3K times 1 milliamp, which is 3 volts. So I have 2 volts, so 5 volts being dropped by 2 volts, and then 3 volts, and come back to 0 volts, because 5 only has 2 volts and 3 volts in there. Get the current first. So everything will be super easy to calculate. And now let's look at one current divider example, then we will wrap up this lecture one, fundamentals of voltage and currents. We are pretty much done. If there's no any other supplemental video can be covered in the future. There might be some. If I see some significant issues in your homework turn-ins, I can give a review session and record it and upload to the YouTube channel. But hopefully, the 3 parts of this lecture one can cover pretty much everything. So now let's look at one example of the current divider. Right. So here's the current. two resistors grounded. That's I equals to 15 amps, and R1 equals to 10K, R2 equals to 5K, and of course the overall current flow to this point is going to be split into two currents. This is I1, this is I2. So if we, just don't think this is complicated, let's just use the current dividers equation since we know that it's going to be right. So I1 equals to I times, right, R2, because I1, you want to put R2 on the top, and over R1 plus R2, which is 15 amps times 5K over 10K plus 5K, right? So it's going to be 5 amps. So amp, remember amp, it's actually ampere. That's the unit of the current, right? So that's 5 amps. And I2, of course, equals to I times R1, right? R1 plus R2, which is 15 amps times 10K over 10K plus 5K, which is 10 amps. So you can see that whenever, actually, if you have a larger resistor, right, a larger wait, which one's larger? So larger resistor, you're getting a lower current, and with a lower resistor, and you're getting a higher current. It's totally because current equals to V over R, and they have the same voltage as these two nodes. So that's why if you get a larger R, you get a smaller I. Okay, hopefully that makes sense. And that's everything about this part of the lecture 1. I'm going to see you in the next video.